Welcome to this session, and I am Jason Wang from Red Hat, and mainly I'm doing the maintenance for a Cameo network system, and also I'm a kernel maintainer for Kubernetes host. And today I would like to share with you how to use eBPF to create an efficient and based on the kernel data path for the virtual machine. So let's go to the outline. This is a review briefly first, and we will discuss the current status of the problems and issues faced by kernel, and then we will have a brief introduction to eBPF and XDP, and followed by simple usage examples of XDP, and finally we have the advanced topics about how to introduce XDP into production environment, and also the current development status and QA. This is a graphic which is very typical for the kernel-based virtual machine structure, and virtio is basically the physical signal for communication between host and the virtual machine, and we also have a backend virtual snack, and it will connect with different virtual devices, and the simplest is tap, and we are using tap to combine with bridge and UVS and connect it with the other physical interface. And in simpler scenario, we'll simply use magnet tap, and it's closely coupled with foundational physical device. And in this slides, we mainly talk about the issues we are facing. For example, efficiency. First, you know that the kernel-based environment is pretty insufficient and not very efficient, and slower than the user-space data path. If you're only using PPS, then we can only get 10% of the user space, and if you're reading through all the codes, then you can easily understand it, but still there are a lot of barriers to overcome, and flexibility is another issue. And we can easily imagine this. If we're adding this new feature, then we have to develop in different kernel modules and in different levels. For example, we have to redevelop and do debugging and optimization for kernel, QUME, and host. And if you're doing this development on kernel, that will be a bit difficult and a bit challenging, and the development for new features is a bit slow, and we are seeking a path, just like updating firmware, like what physical NIC did. So eBPF come into play, and it's pretty efficient, very secure in kernel virtual machine. To the right, we can see this is the eBPF code, and we have generic computing definition and other thread code, and it will be imported into kernel and attached to fixed cook point that will drive the firmware. And eBPF is basically an expanded version of BPF, like the previous speaker mentioned. It's evolved from the classic BPF, and it's simply like interpreter, and it's more effective compared with cBPF, and there are lots of expansions. For example, they have more registers and more instructions, referencing on x86 and ARM platform, and we have lots of LLVM backend, and we can easily reflect the eBPF code into ARM or x86, and we allowed more user space, and cBPF can only filter the packets, but eBPF can also do the same, but we will abstract it into context. And for both reading and writing in this environment, basically we are doing reading and writing for the context. If we're only considering the network, basically we're reading and writing on the packet, so we can produce just-in-time code, and it's pretty secure, and we have a verifier in kernel, and we will minimize the risk of deadlock, and it's very efficient. And in all the mainstream structs, it's the most efficient when we're compiling the code into the form that we want. We can also do BPF syscall for managing program. So this is what I've introduced. How can we run a eBPF struct? And so let's speed up. First, we have a C program, bpf program.c, and we will compile it into bpf program.o using LLVM or Clang, and then we'll have a loader that we will do syscall in BPF, and then we will transfer it into verifier, and then transfer it to JIT, and if we don't have a JIT, then we will directly run the BPF program attached and run. And we'll also have one limitation. We were using map, which is predefined data struct, and also the user control program will borrow user program and inject it into different points, different node. For example, into socket, case point, kprobe, trace point, etc. The most important is TC and XDP, and another major change is that it allows the exchange with kernel, and we can call the other defined helpers from kernel, and we can bind it with kernel struct. And SDP is in the story. You can attach it into different points. This point is a early stage driver, and upon seeing this packet, we will give it a flag marking the XDP value, and then we can analyze and decompose this packet, and we will have different cafe level and value. And for example, it reflects as a drop, then this packet will be dropped, and otherwise it will be transmitted to the external through the same interface, and or it will be dumped to traditional network stack for further processing. And we can support the redirecting of this packet, and we can also use the XDP to transform this packet to other interface. And if it's socket, then we will process the packet with the customized program. And XDP is a basic eBPF program. It's a fully self-defined and fully customized and configured program, and we can upload it into SmartE. It will be more efficient even. Now let's see why XDP is more efficient and more flexible. Again, it's an early stage hook point. It's not entering, the packet is not entering into the traditional stack, and it's blessed with a lightweighted metadata, and they only have several fields, and it can be embedded into the head of the packet. And also we have driver specific optimization, doing some simple assumption, and we can do circling on pages. We can use the driver specific methods and page hook and batching. The batching is not available for traditional stacking, but available here, and we can also upload it into SmartE. And flexibility has to do with its structure. It's not a complete bypass kernel structure, so it was designed to interact with the existing struct. We can use the current network stack, configuration, visibility, debugging, and TCP/IP protocol stack, router, and transmission struct. They can also help with the transmission of this XDP. We will not provide any ready-to-use strategies, but we can use all the strategies in map and existing kernel and routers, and then we can transmit it and will also provide a very good format. And when the driver is not supporting the optimization of XDP, we can do it in XDP level. The performance might be damaged, but the function remain the same. And about how can we help in the virtual environment, we can use tab and XDP support processes packaged earlier, and we have redirected XDP frames between tab and another XDP cable NIC to accelerate host data path and transform the packages, and we can speed up the XDP proc. And we have tested 5 data paths. First, the guest TC and traditional host XDP data path. So we can see the performance is not very good, and it's basically the lowest. So it's less than 2 MPKs. And the second is we replaced it with guest XDP, so we improved slightly the performance. And the third is that we're doing the guest XDP fast redirect on host, and the performance has been improved dramatically. And the fourth is that we're using XDP plus XDP redirect, and we shut down the SMAP, and we're using Linux Next and NOSMAP, and we are now reaching 6.5 DPS, and on max swap we reach 3.5. So we can do a lot of things in this regard, and we are still considering high-level features. First, the eBPF filter, and basically in production environment we are using lots of IP filters, and eBPF is based on backend for IP tables, and in upstream communities they mention this BPF filters, and it's basically based on eBPF. And what did it do? It will have the rules translated into an eBPF based backend and attached it into different native environment. It could be native, upload, or generic, and this is the general principle. And if IP table need to establish new rules, then the BPF kernel can intercept the establishment of rules, and they will also create a helper based on the customer's needs. And the main function is that we'll extract the rules of IP table, then it will again become based on eBPF backend and based on the support of eBPF, and we will inject it into native ICP or hardware. So the structure is already here, but we need to add more details to it. So why are we designing into a client-based struct? So we want to minimize the possible attacks, and also only skeleton merges. We need main logic, and the main logic is RFC, and we are now based on SKD IP table, and we have to transmit it into offload structure and offload environment, and it's very efficient as a solution. And this is pretty interesting. Like I've discussed, attached an STD program, and it has its own logic for processing of the packages. And there are other issues. For example, we have to minimize the load casted by virtual machines. So what can we do? How can we guarantee that SDP program is operating on host? And we need to minimize the load for virtual machine. And XDP, as we know, is based on the logic that can cooperate with generic XDP and traditional data stack, and we can use XDP top. And if it's on host, we have a hardware available, and we can continue to upload the program into Smalley. And how can we do it, and why can we do it? For example, eBPF is a self-contained definition. It's very flexible. So on map level, it's easy to transmit it into a host. And how can we do it? We transform it into eBPF command host, and we can first do the eBPF system call and bound it with an interface, and eBPF will capture this request, and we will translate the name for eBPF into XDP style, and we have a further offload to hardware, and we will inject the program into tab and macro attach. And if the customer program wants to visit the map, they will also follow the process. eBPF proxy and internal helpers are available options, and gateway. As long as the semantic environment is the same, we can also using the packet analysis highway to process the packet on the host machine, but there are other limits. For example, we have different kernel helpers, won't allow all kernel helpers to be borrowed and be scheduled, and we have verifier. We will filter through all the ETL programs that's not meeting the standards of offload. So by doing this, we can easily form a service chain and offload SCP program will only process the JIT package filtering, and we will reference on different levels and different type of headers, and we'll process all the packet on backend, and it's zero topic in the process, no load casted onto the map, and if we cannot finish with the processing, then we have to redirect all the unfinished packages into the system, and we have to redo the whole progress. This is the whole procedure, and this is the service chaining. We have tested different data paths. Let's focus on the number 4. We load the SDP into tab, and we reach a maximum performance of 11 mph, and on map we can reach around 6 mph, and we are using pass-through mode, then we can reach the same level, the same performance just as the native host. XCP, how can we support the temporary device, for example bomb team? And one feature is that you rely on the fundamental device to reflect the logic. For example, failover, VS, and software transmission. If the device is unplugged, we have to switch to the software side, and in the physical device we support XDP, but it's not necessarily using XCP to calculate all the complex logic.
So it's on this stack device and in the specialization machine. We can see this bomb, it has one ethno 0, one ethno 1. So we can use the tab, and we cannot to copy all the program into this bound. So it's hard to do the virtualization on both the ethno and the bound. Also we cannot transfer this to the SDP Pro in this virtualized environment. Bound can also be working in the SKP, and in this environment it relies on the generic auxiliary. Auxiliary is expanded to the XP. We can make the XP you need to use X handler to treat the XDP's proc and to transfer all these frames to the stations. And in these stacked devices, and not all the logic can be realized in SDP, but we have SDP path. And when the logic is very complicated, we can use it in the traditional path to deal with it. This is a POC performance is realized in the Mac-VLAN. And if we just do this GUSP, you can see this level of MMPS. And if we reach it higher, then we can see the 10. This marked in yellow because the Mac-VLAN is on logic. We need to search for its Mac-VLAN on address. Another is OVS XDP datapath. The kernel has accelerated SDP. So how can we use the data path to accelerate the current on data path? One is to TC flower data path. Use the XDP to realize the TC flower, to use the control to control the different data paths. And it's like we need to offload the flow from the original one to the destination. We need to offload. We just need to bypass the kernel path. We can realize the XDP flower. We need to translate this offload program and to use the SDP program to make it mapped to the SDP. But we cannot realize all the logic with this SDP data path. If we cannot deal with a lot of complicated issues, we can use the SDP path and focus on traditional data path. But all should be realized through XDP data path. And recently, they have released a lot of information that they can, because of the size of instructions, some limitations will be relieved. And this is FXDP. And we have discussed in previous discussions, we can treat it as an F packet based on XDP. And compare, it is based on edge map. It means that it has its own ring layer. And it's attached on the specific line for the package receiving and sending. It doesn't rely on XDP. And based on this original patch, it can have a 20 times performance increase. This ring layout is moved from virtual 1.1, and we like to combine it with the virtual 1.1, and there are two modes. One is zero couple. They need to have the support of the driver. When the zero couple is enabled, the VF SDP, they will be translated into the file that can be known by the descriptor. And they don't need the data package copy. One is generic. It doesn't need any support from the driver, but it's very slow. It's based on the slow XDP. It has limitation. It uses UMAM. UMAM means that the SPD socket can only be read and write in a certain specific region, and we need to use the memory to make it stored in this memory. And also the largest size of the packet is about 2K, and the metadata is very simple. It cannot support very complicated tasks such as offloading. So how can we apply the AF in VM? So it had how can we expand the OVS? We have this device. It is FTP socket. If we XDP socket, if we attach it to the, we can realize there lies this virtualized data path. And if you print it on the physical NIC, we can see this data path for this NIC. But you can see there's a lot of issues here. So you can use the vhost user to have a high efficient route. If you want to go to the root, you need to realize the freedom copy of the tab. And we are thinking about how to make good use of the AF XDP. We put forward this AF XDP passthrough. It was brought from the net map passthrough. That is one to how to make virtualized machine to control the host. We introduced the ASKPT device. Once the application, the socket is generated and expounded to this device, then the instructions and all the original data will be transferred to the backend, and the socket will be generated. And all the XDP, they can all be stored, but this application is just activated as the backend SDB. So it can achieve the same performance. So it's just responsible for some startup, stop, and configuration. These very simple tasks. And the eBPF-based vhost data path we need to deal with, because we are developing different ring layouts. And the different ring layouts, I think it's very complicated and painful. And we need to requires migration for the bug fix. And when the new ring layout requires a lot of hard work, so we think that we can decouple the ring layout specific code out of the kernel through eBPF. I mean, all the codes related to the ring can be realized through eBPF, so that the new ring layout can be attached to the new EPL program. But we have a lot of issues here. One is the performance and how to realize the batching. And the workflow is similar. When the guest driver accesses a news, and but the peg ring is leaked and to the host. When the XD frame comes to the host, and it will activate all the code, backend code. But we need to design it very carefully. This is status. So bpfilter is only a skeleton, and the virtio-net is just in its original, and it can also be only be realized in native path RFC, and OVS XDP data path. We are building a prototype, and OVS AF XDP path is still RFC, and F2 AF XDP pass-through. The data path, we are still planning it. We need liberal support, and we are still planning it. These are some references. So any questions? Mention that, sorry, the interpreter cannot hear what he's talking about, because he does not have the micro. We mentioned the eBPF. If we want to add a program for it, so is it for the patch for the kernel, or does it compile it SO and to add it to it? So this program needs to be injected into the kernel, and it has the self code. Then through the loader, then it can be injected into the kernel. So It's a kind of the self-code. So if you want to compile a packet, then what form? It's just a binary file. You can package it into all sorts of forms because the binary is compatible. It doesn't need to be released together with the kernel. In theory, it is because eBPF is compatible in terms of the instruction level, and XDP because the examples are based on host and NIC. For the VM, can we realize it? Yes. VM, yes, this is XDP. Yeah, you can do everything on host. You can do it on VM, but it's based on virtual L. XLVF, it's based on the manufacturer's support, like the Intel, they support XDP. So container is another story. It uses the Mac-Blano pair, and you can do the XP program. If you use it pair, then you can support it. It can based on SLR-VF. If you use the Maniloft VF, it can also support it. IP table, it supports different namespace. If we deploy it, including the nav filter, any restrictions? No, they are just management tools. Yes, it can satisfy your needs. There's no change in namespace. It doesn't concern namespace. It can run independently in different containers. Yes. I have a question. When the processing of the pack, we have this high-speed architecture, but the performance, I think the performance is not that good. The XDP is kind of in between, right, in terms of the performance. So, in what kind of a situation where we need XDP? I think DPDK, if you want to MCA applications, XDP for scenarios, you need to connect it to the user. If you want to do the DDoS, a load balance, this is based on the traditional protocol that is very suitable. Facebook has its own pure XDP. It will be passed through its own load balance. I think XDP is very suitable when in terms of its advantages, we don't need to deploy another one. It's about choice. If we focus on the performance in the DPTK, it's better than this. But if we want to focus on other areas about the balance of the performance, then XDP is a good choice. Yeah, when a DPTK cannot satisfy the needs, you can choose the XDP. Yes. Yeah. Because DPTK, they need to be connected to the OS. So I think XDP, we are still optimizing it. We want to make it as fast as DPTK.
So I can see that there are X ChatDP passed through the SDP, and yes, it didn't get us the performance data. Why? Well, this is still in plan. You can reference on net pass-through, and they're just the same as directly doing map on net map. So it's already supporting this, but KMU support is not secured. So on tab, if we're using this one, then we need the tab to support zero copy, and if we want to bypass tab, then we have to wait till you change the ring layout and directly put it on your new ring layout. Will it be better, or we convert it directly on XDP and put it in VHR ring? Well, is there any better way? Well, I think the so-called better way is just an option. You can establish your own vhost user. So this is not the most optimal way. So basically, it's not the best way that we can think of. Okay, one question from me. You mentioned that there's a limits for the loop in kernel, so XDP, when we're doing the KZM, and like Facebook, they are only conducted on the 4th layer, so XCP has limits. In the future, we will do more work on it. For example, make sure the metadata can support XD and check some loam, and that might help you. Well, for the loop, the upstream, or we're still doing bound pathway, and for example the volume is fixed, for example 1.4 thousand. If it's convertible, then we need some tricks, and we can break it using our compilers. And well, you can introduce a kernel helper, a generic kernel helper, for example checksum, and we can make sure the system call on the kernel helper, and that there will be no limitations for you. You can run all the tests you want. Okay, time's limited. Time's up. So any questions, you are more than welcome to come privately. Thank you.